Hi everyone. Today I'm going to be talking to you about regression analysis with time series data. So this is what the classical linear regression model looks like right here. We've got the response variable y that is expressed in terms of two components. Uh, this portion here represents the explained variation in y, and that is the linear equation relating the response y to the predictors x over here, and of course multiplied by some regression coefficient beta of j. And then here we have the other component uh, that contributes to y, and that is the random error or the error terms, so that it accounts for the unexplained variation in y. And of course, after applying the least squares method, we should obtain the best possible um, regression coefficients for the beta j's over here, right? And so this goes on the basis that the error terms, of course, are normally distributed with zero mean and constant variance sigma squared, and that they are also independent of each other. But now the problem is that um, when we're dealing with time series data, we're often looking at daily, monthly, quarterly, or yearly data. And then how do we interpret the regression model results on data over here that will perhaps exhibit trend, seasonality, or any other time-related pattern? An estimated regression model, let's not forget, is built on the basis of a random sample of observations. But this basis is violated the moment that we start to deal with time series data, as observations in different time periods are related or autocorrelated. So in regression analysis, it is assumed that the error terms are independent or uncorrelated. And hence we have here this property that the covariance between two consecutive error terms will have a value of 0. And so we see no autocorrelation in the errors, no patterns in the errors, and this is what a time plot of the residuals should look like, exhibiting here some the property of randomness. Okay, so of course, when these properties are met, then the application of the least squares criterion yields meaningful statistical results. And so this means that the y values should be related to the predictors, but not to one another. So here we have time series data um, where here the assumption of independence um, rarely holds. Okay, so in other words, here we're looking at um, a pattern in the residuals, perhaps, right? There is some sort of a pattern in this time plot of residuals. To give you an example, this is quite common, in fact. To give you an example, take a look at car prices, where from one year to the other, we can see that the prices are in fact autocorrelated. So the car price for this year is, somewhat dependent on the price of the car in the previous year and 2 years before, and sometimes even 3 years before. So this here is what causes the assumption of independence in the y values and hence in the residuals to be violated. So here we have to beware of spurious regression results. Spurious regression results here imply that the estimated coefficients for the regression equation are incorrect, right? If they are going on the basis of the method of least squares, well, that method of least squares no longer applies here. Spurious regression results also implies that the predictors appear to be better than what they really are. So looking at the statistics on the predictors here, you might see that the p-values are extremely small, giving the impression that these predictors are very significant in explaining why. But that is also false. And of course, the standard error of y, well, that will be either underestimated in some cases or overestimated in other cases, and so that will distort the true standard error of the regression model, hence distorting all other measurements that rely on the mean squared error, such as information criteria measures. Here we see how autocorrelation, in fact, is categorized in one of two categories. Here we've got positive autocorrelation. The thing to notice with positive autocorrelation is that we see the pattern of positive error terms followed over time by other positive error terms. So we can see here, this is a scatter plot, yes, a time plot of the error terms, and we can clearly see that there is some pattern over here. This is as a result, of course, um, after observing greater than expected y values, followed by greater than expected y values, right? So as a result of that, we see how the error terms are increasing over consecutive time periods. Likewise, we can also observe uh, negative error terms that tend to be followed by negative error terms. So we would see that right here. And so as a result, when we do a scatter plot of two consecutive error terms, so E of t minus 1 plotted against E of t, we see this type of pattern in positive autocorrelation. For negative autocorrelation, it's rather the opposite that is happening over here. We see that we have we have positive error terms followed over time by negative error terms. So we have this effect of a jagged um, pattern over time for error terms, right? And the corresponding scatter plot of E of t minus 1 versus E of t gives us this type of shape over here, this overall shape. Okay, so what about here now when we look at, sorry, so when we look at the no pattern autocorrelation, well, finally, the no pattern autocorrelation, well, that is what we are striving for. That is what we want. So we want to find error terms that over time do not show any systematic pattern. So really exhibiting randomness over here, and hence a scatter plot should look like this over here of two consecutive error terms being plotted. So actually, let me just go to this example over here. So here I want to show you how um, um, a positive autocorrelation can affect the results of a regression model. So what we see over here, in the first place, that solid black line is the true regression line. This is what is really happening with the data. Once we know, of course, that we're dealing with time series data. But if we do not recognize that feature about the data, and we treat it like normal data, like a random sample of data, and we try to fit a regression model on that data. Well, this is what we would get, right? We get this fitted regression line, which of course by method of least squares attempts to find the best fitting line which will minimize the vertical distances um, of each point relative to the line, right? And so we get a line that seems to cross um, fairly well so as to have about an equal distribution of points falling below the line and points falling above the line, right? That's what the fitted regression line does. But in reality, the true regression line is showing that, there is um, a whole group of points that are really falling above the line for um, a period of time. And then we find another pattern where these points tend to follow each other, where they fall below the line, right? So you do see here that there is in fact a pattern going on. So we want to get rid of this problem in our regression analysis in order to get a proper regression analysis. So this equation here, which is the classical linear regression model equation here, we now want to break it down into its proper form. In other words, we want the error term here to be expressed as what it really should be, and that is that it depends on the previous error term. So E of t is in fact a function of E of t minus 1. And here we want to um, express E of t as a linear function of E of t minus 1. So we get this equation right here. E of t is equal to rho. So rho over here is a coefficient, not just any coefficient, it is the um, correlation coefficient for population, okay? And that is multiplied by the previous error term, plus this now new error term that we define. This is now the new error term that will define the original error term. This new error term, call it nu of t. So more on this equation right here, in fact, this equation, this linear equation here can be considered as a first order autoregressive model equation. Hence, it is an AR1 process. Okay, and what it is doing is regressing the error term on itself. So autoregressive, a model of residuals. It is also called the first order serial correlation. Okay, because here we are talking about the error terms. And so rho over here, as I mentioned before, is in fact the population um, correlation coefficient. And nu of t here is assumed to be the new normally and independently distributed error term with mean value 0 and constant variance sigma squared of nu. Now, just very quickly here, I want to remind you that the correlation coefficient lies between -1 and +1. Um, and it measures basically the linear relationship between two variables. In this case, we are measuring the linear relationship between E of t and E of t minus 1. And rho will equal 0 when there is no autocorrelation on E of t versus E of t minus 1. Or in this case, epsilon, of course, because we're looking at population parameters and population random variables over here. Um, And so when that is the case, interestingly enough, when rho is equal to 0, if we go back to our equation right here, that would mean that E of t is equal to, well, 0. We get 0 over here plus nu of t. In other words, when there is no autocorrelation on the error terms, then the error term is really equal to this error term, which has all the good properties for a regression model. When our rho here is greater than 0, then we're talking about a positive autocorrelation going on in the error terms. Positive autocorrelation, very quickly, let's just look back. This is the type of pattern that we're looking at in a scatter plot. The relationship between two consecutive error terms would have this type of pattern right here for positive autocorrelation. When rho, of course, is negative, then we're talking about negative autocorrelation, in which case the two consecutive error terms would exhibit this type of pattern over here. Of course, when we talk about autocorrelation, um, we must also bring up the topic of covariance between two um, consecutive error terms, right? So a positive autocorrelation implies a positive autoregressive model of order 1. And when the correlation coefficient is negative, then that means, of course, that the covariance between two consecutive error terms will be negative as well. And so here we are looking at a negative autoregressive model of error terms of order 1, or negative serial correlation. Okay, of order 1, yes. Okay, of course, it is possible to look at higher order autoregressive models on the error terms. Uh, and so if we talk of a lag2 autoregressive model, then this is the form that we get. So here we see that the error term is expressed in a linear fashion um, in terms of epsilon of t minus 1 and epsilon of t minus 2. So it goes back as far as 2 time periods over here. And the same applies when we're looking at autoregressive models of error terms of order p. So here, epsilon of t goes back as far as epsilon of t minus p. To give you an example over here, we see how we've got a very simple example of consumption, and we want to express it in terms of income. So let consumption be your response, and income is the predictor. And here we have, of course, in our regression model, of course, we always want to have the error component in there as well. So we would expect that the error component really exhibits all the four model assumptions, that is normality, independence, zero mean, and constant variance sigma squared. But we notice here that in fact, the error term of a given year over here, say the year 2000, is related to the error term of the previous year. And further, when more investigation is done, we realize that this error term has in there an element that is not contained in the income, and that is the tax rate. So if you realize now that the error term is in fact mostly made up of tax rate, then we can understand how tax rates, are dependent on tax rates of previous years. So that makes a lot more sense, right? Now we start to understand why there is this dependency in the error term, and that is because the error term um, is mostly made up of tax rate data, which was not explained by the income. So in that case, we can uh, ex um, break down the error term into its different components using, of course, a first order serial correlation model or first order autoregressive model. Okay, so in this case here, um, we say that the tax rate of a given year is linearly equal to the correlation coefficient um, of the tax rate at year t versus the tax rate at year t minus 1. So this is the correlation coefficient right here that is multiplied by the tax rate of the previous year, um, plus of course the error component right here of the time t at time t. So in this case at time um, t equals 2000, the year 2000 over here for this example. And of course, we call this new error term, we call it new. Okay, so that is the form that it takes on, coming from this first order serial correlation model. Okay. Here we see, of course, just a reminder of what are the consequences um, when we apply autocorrelated terms in our linear regression model. Well, we see that, the estimated model may infer an overall goodness of fit that might look too good to be true, right? So the F statistic might appear to be larger, might be larger than what it should really be, right? And then, of course, we have all these misleading inferences, what we call the spurious regression, which is implying here that we've got statistically significant predictors. The standard error of y appears to be better than what it really is, etc., etc. Hence, again, a spurious regression. So there must be, some type of way to avoid this problem, running into this problem. How do we detect this problem over here of autocorrelation in the error terms? Okay, well, before actually, we did look at the Young box statistic, um, or the Q statistic if you want, which is there to detect the presence of autocorrelation in your data, in your residuals, in fact, in your residuals. So here, I just want to review with you the form of a Young box statistic. This is what it looks like. This is the Q statistic. And as you can see, it is a function of the sample correlation coefficients over K lags, over K time lags, squared and divided here by N minus K. That is the form of the Q statistic multiplied here by some coefficient. And the idea with the this test statistic is that it is applied to a to test out a null hypothesis. The null hypothesis here is stating that for all time lags from 1 to k, we are saying that there is no autocorrelation in the residuals. Okay, and the alternative states otherwise. It says that there's at least one time lag that has autocorrelation over here. So if we go to the null hypothesis once again, we are saying basically that the model is adequate, versus in the alternative hypothesis, we say the model is inadequate. And we test the null hypothesis at a level of significance of alpha. So if my alpha here is at 0.05, then when I look at my Q statistics over here and their corresponding p-values, I want to see if my p-values will be smaller than my alpha of 0.05. My p-value, of course, being 0.05, and if I get p-values here in my sample that are less than 0.05, the idea is that I reject the null hypothesis. And if I reject the null hypothesis, then this means that my model is not adequate, hence it is inadequate. So let's not forget again that the Q statistic will measure over several time lags, right? So the first set of lags is the first 12 time lags, in which case here I am getting my Q statistic right here of 20 over the first 12 time lags, and I am getting here a p-value of that is in fact inferior to the level of significance of 0.05. What does this mean? It means that my first 12 time lags are autocorrelated. There is in fact autocorrelation in there. And so I must reject the null hypothesis. My model is not adequate for the first 12 time lags, right? Beyond that, of course, well, it's kind of pointless at that point because, if the first 12 time lags give me an inadequate model, then I don't really want to pursue beyond the 12 time lags. Yes. Okay, so that is for measuring autocorrelation in the residuals. So we can do that, but of course, with the Liang box statistic, we see that it is done in groups of usually 12 time lags. But what if I'm not interested in looking so far behind? What if I don't really want to look at up to 12 time lags? What if I'm only interested in only looking at the first um, time lag? I want to know if my residuals are autocorrelated in the first time lag. So that is what the Durbin-Watson test takes care of. It looks at, it determines whether there is a first order serial correlation. And so here lies the null hypothesis. We say that the correlation between epsilon of t and epsilon of t minus 1 is non-existent versus the sorry the alternative hypothesis, which is saying that there is some correlation between the first two epsilon, so e of t, sorry, epsilon of t and epsilon of t minus 1. And the statistic here that we use to measure this claim in the null hypothesis is the Durbin-Watson statistic, which is this formula right here. So as you can see, we are looking at our sample data, looking at sample error terms, and measuring the difference between two consecutive error terms, squaring that deviation, and relative to here the sample variance, if you want, of my residuals. Okay. So the Durbin-Watson statistic is compared, of course, to a critical value from the Durbin-Watson distribution, which I'll show you in just a little bit, where, of course, we need to specify over here the level of significance alpha at which the test is conducted, the number of observations that we're looking at, so that's your n observations or your n residuals in this case. And of course, we need to know how many predictors or regressors we're looking at in the model, right? So I'm going to show you very quickly here what a Durbin-Watson table looks like over here. So here we've got one for an alpha of 0.05, and you can see how there is a Durbin-Watson distribution for each sample size over here, n. So I've got a different distribution for each n value. And I have here a pair of lower limit and upper limit Durbin-Watson statistics. So note that for each value of k, so k here being the number of predictors in my regression model, I will get two critical values for a given k. One for the lower limit of the Durbin-Watson and one for the upper limit of the Durbin-Watson statistic over here. And you can see how here we also have another set of Durbin-Watson critical values for another level of significance, this one here being 0.01, alpha is 0.01. Okay, so let's go back to the slides. Yes, so we continue right here. So here, we just a note here is that when we're dealing with business or economic data, well, most oftentimes we're looking at positive autocorrelation. So if we're dealing with positive autocorrelation, we now narrow down the Durbin-Watson test to be, instead of being two-sided, we now look at it to be one-sided. So we say in the null hypothesis that the the correlation coefficient is equal to 0 versus in the alternative, it is greater than 0. Okay, so that is on the assumption that we are dealing with business time series data. And so, of course, we estimate the population correlation coefficient with sample correlation coefficient, and that is R and R of 1 because we're looking at a first order correlation over here. We're just interested in the first order autocorrelation between consecutive error terms. And so this follows this form right here. This is the formula right here. So I just want you to note that in fact here we are multiplying the error term at time t times the error term at time t minus 1. Okay, please note this formula right here. And the error term at time t is in fact just the difference of the observed yt minus its predicted value, right? That is how the error term at time t is defined. Likewise, the error term at time t minus 1 is the difference between the observed y at t minus 1 minus its predicted value at time t minus 1. So in fact, here we are looking at the product of two deviations. Okay, so this is really the product of two deviations. And in the denominator, well, here we are looking at the uh, sample variance of the error terms of the residuals. Okay. Um, so yeah, so a sample variance of the residuals, or if you want the variance, the sample variance of the observed values of the y, sorry, of the y values relative to their predicted values. Okay, so here we are. This is just a little recap on what the correlation coefficient formula is. Okay, let's continue on. Okay, so we say that for uh, moderate to large sample sizes, so moderate here would be, anything that is 40 and above is considered moderate to large sample sizes over here. Then we can equate um, the Durbin-Watson statistic here. There's just one little mistake. This should actually be a product. Okay, so this is, let me just go back. Oh, No. Okay, no, this is correct. Sorry. This is correct. So yes. So here we have the difference of the error terms divided by the sample variance of the error terms. Yes. So for a moderate to large sample here, we say that it is approximately equal to 2 times 1 minus the correlation coefficient for the sample. And let's not forget, of course, that the correlation coefficient lies between -1 and +1. Okay, and in positive autocorrelation, what will happen here in the numerator is that we'll see that successive residuals will tend to be alike. If they tend to be alike, then the value that we're getting here in the numerator will be relatively small. Okay, to elaborate more on this statement right here, we can now, kind of play with this formula, this relationship here to now come up with the following relationship, and that is that the Durbin-Watson statistic divided by 2 is approximately now equal to 1 minus the correlation coefficient for the sample. And if that is the case, we can now equate the correlation coefficient to be equal to 1 minus the Durbin-Watson statistic divided by 2. Now, if we know that the correlation coefficient lies between -1 and +1, then we can deduce from that that the Durbin-Watson will lie between 0 and 4, right? Because, in fact, when uh, the correlation coefficient is equal to +1, we get here 2 times 1 minus 1. That gives me 0 in the bracket. And so that tells me here that my Durbin-Watson has a lowest value of 0, hence the 0 right here. When my correlation coefficient is equal to -1, then here I get in the bracket 1 minus -1 gives me +2 times 2 gives me a maximum value for the Durbin-Watson statistic equal to 4. Hence, the Durbin-Watson lies between 0 and 4. What are the decision rules for a one-sided Durbin-Watson test? Well, that's pretty straightforward. We say that if the computed Durbin-Watson happens to be greater than the upper limit of the critical Durbin-Watson value, then there is no positive autocorrelation. Okay. Um, So in other words, we do not reject the null hypothesis over here. Let me just move on to the next slide, and you'll see a little bit more what this means. So this is what is going on. So here we have our critical Durbin-Watson statistics. Of course, remember they always come in pairs. So we've got the lower limit value and the upper limit value. And so as I was saying before, if your Durbin-Watson statistic is greater than the upper limit of the critical Durbin-Watson, then we conclude that there is no autocorrelation, hence we do not reject the null hypothesis. Should my Durbin-Watson statistic be less than the lower limit of the critical Durbin-Watson um, uh, value, then in this case here, I conclude that there is some positive autocorrelation between two consecutive error terms, and hence I reject the null hypothesis over here. Now, what happens when my Durbin-Watson statistic lies between the lower and upper limit of the critical Durbin-Watson values? In this case, we say that the test is inconclusive, and we need to further analyze the residuals in order to, come up with a better solution. Perhaps we need to add a predictor to the model. Uh, Maybe we need to investigate the autocorrelation coefficient some more. Okay, so that is basically how you conclude over here. Another interesting thing that I just want to point out is that when you need to further analyze the residuals, Um, Keep in mind, of course, that if the sample correlation coefficient lies in the interval between 0 and plus or minus 2 over the square root of your sample size, then you conclude that the autocorrelation here is too small to be statistically significant. And hence, we do not reject the null hypothesis that there is some positive. We do not reject the null hypothesis, and we say that there is no positive autocorrelation or no autocorrelation period. Okay, this is an example uh, here where a regression analysis was conducted on time series data. We have here one predictor. The sample size was of 40, and these are the results that we're getting over here. We're seeing here that the predictor um, has this value right here and for the coefficient, and it has a p-value that is indicating it is statistically significant in the regression model. It's giving me good statistics over here. The Let me see over here. We look at the F statistic indicating a very good fit. The model, the data fits very well for this model over here. We are getting a very good fit. Um, and My R square here, okay, so my R squared is telling me here that it is pretty high. In fact, X and Y are strongly related. They are moving together, and hence my R squared value here is very close to 1 at 0.9584. But further in this output, what is interesting is that I'm also getting in this output here a Durbin-Watson statistic value. So not all statistical packages provide this information. You can get it in Minitab, however, if you set up your analysis, your regression analysis to give you the Durbin-Watson statistic. And you can obtain it, of course, in SAS. And I'm not too sure about R. I'm sure you can get it through R. But in any case, I'm getting here, interestingly enough, a Durbin-Watson statistic of 0.122. Okay, so what does this mean? Well, I need to go and compare it to the critical Durbin-Watson values for um, an alpha, say here of 0.05. I'm going to use an alpha of 0.05. I'm going to look at my sample size here of size 40, and I have one predictor. So in other words, I want to look at the corresponding critical Durbin-Watson values for alpha is 0.05, n equals 40, and k equals 1. So if I go to my Durbin-Watson table once again, let me just scroll down here and okay. Actually, I do not have that information available. If I were to look at it for an alpha of 0.01, if I were to do this test for an alpha at significance level of 0.01, by the way, you can get the corresponding critical values for your Durbin-Watson at alpha at 0.05 if you look in your Durbin-Watson tables that I've posted for you guys. So you will find it. But at 0.01 over here, and at a sample size of 40 and k equals 1, I see here that I've got critical values of 1.25 and 1.34. Well, if we go back to the decision rule, we said that when your Durbin-Watson test is less than the lower limit of your critical Durbin-Watson value, then you reject the null hypothesis. And so, in fact, we have here a Durbin-Watson statistic of this value right here, clearly less than this 1.25 that we're getting in our table at an alpha of 0.01. And so here we must reject the idea that there is no correlation. In fact, there is some autocorrelation going on. So if there is autocorrelation going on, we move on to the next step, and that is to equate over here the error term in terms of its previous error term. So we have this autoregressive model of order 1 for the error terms. And so now we must find this coefficient here. What is this coefficient for the predictor here, epsilon of t minus 1? So this coefficient here is in fact this quantity right here. So now it's like I'm doing a little regression model without an intercept in order to get my rho estimate value. So my rho estimate value here is 0.9142. And, um, and so I see here that I am getting significance in my predictor. It is telling me that my predictor is significant. And I see here, okay, so let's just go look at the Durbin-Watson statistic that we now get. So the new Durbin-Watson statistic that we're getting is of 1.472987. This is for this regression model, if you want this. Consider this a simple linear regression model without an intercept. And so I'm getting good results. My Durbin-Watson statistic is clearly larger than it was before. Let's go quickly look at the um, critical values for the Durbin-Watson at a level of significance of 0.01. So for a value now, remember, because by now looking at the residuals, what happens is I have now lost one observation. I have lost one row of observations, right? So I am now looking at 39 values and not 40. That is my new N. I still have one predictor. So when I look over here, I'm going to look at row 39, and my critical values are 1.24 for the D of L, and sorry, 1.24, yes, and 1.34 for the D of U. And so I see clearly that my Durbin-Watson statistic is greater than the upper limit of the critical Durbin-Watson. So let's just go back over here. And so here I see that I've got, um, I have over here a Durbin-Watson statistic that is greater. Let's just go up. So I am in this zone right here. You can see that I'm in this zone, and so I do not reject my null hypothesis. So there is no evidence of autocorrelation over here. Okay, so that is how you do it over here. I just want to walk you through an example also that I wanted to add in. Um, so here you've got another example where you've got your sales and your income, and a scatter plot here shows you how X and Y are related. Okay, this here would be the fitted regression line for my sample, and this, of course, would show me uh, the line that best fits across all points, minimizing, of course, the vertical distances of each point relative to this line, of course, but that does not necessarily mean that this is really the best line for X and Y, right? Because if indeed I have autocorrelation in my residuals, then this regression line is meaningless. Okay, so let's look at the results here. If I were to treat my data here as normal data, and I plug in a regression equation, this is the equation I would get. These are the statistics I'm getting on my equation. So I can see that my predictor is statistically significant with very small p-values. My correlation coefficient over here um, is, sorry, this is my, yes, this is my um, coefficient of determination, which in fact is measuring how the regression equation here accounts for the variability in y, and I'm getting here a very high value of 90.5%, which is telling me that I have a very good regression line over here. My standard error here is of this much. Um, my goodness of fit statistic is very high with a very small p-value. But now let's look at the Durbin-Watson statistic. The Durbin-Watson statistic here is of this much. Okay, and so when I compare it to the critical values for corresponding um, sample size. So here we have a sample size of 20, and we have, sorry, a sample size of 21. Yes, a sample size of 21. And we have one predictor. If I'm looking at it from a level of significance of 0.05, these are the critical Durbin-Watson measures that I'm getting. 1.22 for my lower limit. And clearly I see here 1.22, my Durbin-Watson statistic is of 0.87, which is, of course, less than, let's go back, it is less than the lower limit of my critical Durbin-Watson. Hence, I must reject the idea that I have um, no autocorrelation. So in fact, I have positive autocorrelation in my data. I have positive autocorrelation in my residuals. Okay, so this is just one example over here. Okay, continuing on. Um, so here, um, if we want to make this linear regression model more representative of what is really going on, then we need to account for the error term, which is in fact another model in itself. It is an autoregressive model of order 1. And so here we can now equate the new response variable to be the result of a differenced variable. So if we let here my response variable now become a differenced variable, and my predictor to also become a differenced a variable as well of this format, we can now express this new regression equation to be of this format right here. Okay, so I provide here in this document here, I provide a little proof on how we go from this form right here to this generalized differenced form right here. And so this is a proper regression model when we have autocorrelation in our residuals. And here we can see that the error term is now really independently and normally distributed with mean value of 0 and constant variance. And yeah, so you can look at this right here. I will post this for you to look at. And so essentially here, what we can say is that you know, when we have no correlation in our residuals, then this rho value here will equal 0, right? And what will happen is that we will have the y of t differenced will now be equal to the beta 1 um, times the x of t. So if rho is in fact equal to 0, then this difference to x of t will now be x of t. And in fact, the difference to y will just be y, right? Um, and on the other hand, when the rho value is equal to 1, um, oh, okay, yeah, sorry, just a little mistake here. So when rho equals 0, then in fact I have my normal regression equation. So I have y of t is equal to beta naught plus beta 1 times x. So never mind this differenced because now I know that when rho equals 0, x differenced of t is simply equal to x of t, and y differenced of t is simply equal to y of t, right? So, so that is in the best case scenario when there is no serial correlation. When there is serial correlation and when rho is in fact equal to 1, so that is the other extreme, then now I am looking at this part of the generalized difference equation to now become 0. This becomes 0. And here um, I have a perfect first order difference. So in fact, I have my x prime of t is in fact equal to x of t minus x of t minus 1, because this here is supposed to be equal to 1. Likewise, the y prime of t is equal to y of t minus y of t minus 1, because once again, this rho is equal to 1. So I have here a first order difference. And so when rho lies somewhere in between 0 and 1, then we have this format over here for our variables, and so we keep this general format for the generalized differences. And so with this, I conclude my lecture on regression analysis with time series data. Thank you.